Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the lecture 29th of Discrete Structure CSC 102. In the previous lecture we have started graphs and we were discussing some basic definitions and notations of graph. Today we are going to continue the graphs, and in the previous lecture we have discussed directed graphs, simple graphs, complete graphs, complete bipartite graphs, and we have just started subgraphs. Today we shall start from the subgraphs and concept of degree. What is the degree in the graphs? So in today's lecture, first of all, as I have told you, we shall discuss first subgraphs and degree of vertices in the graph, and then we shall start walks, trials, paths and circuits. What is the connectedness and connected components? And at the end we shall discuss Euler circuits and how to construct an Euler circuit. So what is a subgraph? You know the definition of graph. We have discussed in the previous lecture. A graph H, if we have a graph, any graph G or H, we can denote it by a capital letter. So here we are denoting graph by a capital letter H. It's said to be a subgraph of a graph G. H is a subgraph of G if and only if every vertex in H is also a vertex in G, and every edge in H is also an edge in G, and every edge in H has the same endpoints as it has in G. So this is basically the definition of subgraph. Every vertex of H must be vertex of G. Every edge of H must be the edge in G also. And one more property which we have to investigate in the subgraphs, that the endpoints of each edge must be the same as endpoints of each edge in the graph G. For example, if we see this graph, the given, this is the graph capital, you can see this is the graph G, and we have to determine, we have to plot, draw all possible subgraphs of this graph G. So first of all, this graph have two vertices V1 and V2 and three edges E1, E2 and E3. E3 is a loop and E1, E2 are parallel edges. So we have to draw all possible subgraphs of this graph. The concept is same as the subsets of a set, as we have discussed in the set theory. First of all, you can see this. These are all possible subgraphs of the given graph in the previous slide. The first subgraph could be V1, vertex V1. This is a subgraph of the graph given this graph G, because it satisfies all the conditions in the definition. The first condition is every vertex in H is also a vertex in G. So V1 is a vertex, it is also a vertex in G, and there are no other things in this graph, that is there are no edges, there are no other vertices. So we cannot check the other conditions, that is every edge must have same endpoints as in the graph G. So this is a subgraph. If we write V2 in the second graph, this is also a subgraph. In third possibility of subgraph is V1, V2, we write two vertices. So this is also a subgraph because it satisfies all the conditions given in the definition of subgraph. The fourth possibility is we can write V1, V2 and E1, edge 1. This is also a subgraph of the graph G. it satisfies all the properties. V1 and V2 are the vertices in subgraph. They are also vertices in the graph G. E1 is edge in subgraph. E1 is also edge in the graph G. E1 has endpoints V1, V2, and in the given graph, E1 has vertices endpoints V1 and V2. So it satisfies all the conditions given in the definition of subgraph. Therefore, it is also the subgraph of G. At fifth number, we can write also a subgraph V1, V2 and edge E2. It satisfies also all the conditions, therefore it is a subgraph. We can write another sixth subgraph is V1 and the loop, and this one is V1 and V2, and we draw a loop on V1. Eighth graph is V1, V2 and E1, E2. Ninth graph is V1, V2, E1 and E3. 10th graph is V1, V2, E2 and E3. And the 11th graph is the whole graph G. It is also a subgraph of G. So these are all possible subgraphs which we can draw, which are the subgraphs of this graph G. You can see all these graphs satisfy all the properties, all the conditions which are given in the subgraph. So this is basically the definition of subgraph, and this is how we can plot, we can draw all the possible subgraphs of a graph G. So next, what is a degree? Degree is basically, this concept is related to the vertices of a graph and the edges which are incident on a particular vertex. So by definition, let G be any graph and V be any particular vertex of G. The degree of V, it is denoted by deg of V, equals the number of edges that are incident on V, with an edge that is loop counted twice. So what is a degree? Degree is this concept basically related to the vertices in the graph. For example, if we are given this graph and we want to calculate the degree of this vertex. Now we have to see how many edges are incident on this vertex. This edge is incident on this vertex, this edge is also incident on this vertex, this edge is also incident on this vertex, and there is a loop which is incident on this vertex. So 1, 2, 3, 4, 5. So loop is counted twice. हम लूप को दो दफ़ा काउंट करेंगे, दैट इज़ ये एज भी इंसिडेंट है और ये एज भी इंसिडेंट है, इस तरह. सो कितने एजेस जो हैं वो इंसिडेंट हैं इस वर्टेक्स पे? 1, 2, 3, 4, 5. सो the degree of this vertex will be 5 because 5 edges are incident on this vertex. So this is basically the concept of degree. And what is the total degree of any graph G? Basically the total degree of graph G is the sum of all degrees of all the vertices of G. For example, in the previous slide we have discussed this graph. What is the degree of this graph? We have two vertices V1 and V2. Now we calculate the degree of V1. What is the degree of V1? How many edges are incident on this V1? 1, 2, 1, 2, 3, 4. So degree of 1 is 4, degree of V1 is 4, degree of V2 is, what is the degree of V2? This is V2. And how many edges are incident on v2, there are two edges which are incident on v2, so therefore degree of v2 is 2. So now what is the degree of the whole graph G? This is basically degree, sum of the degrees of all the vertices, that is, this is degree of v1 plus degree of v2. So this is 4 plus 2, 6. So degree of this graph is basically 6. So this is how we can calculate degree of a graph. What if we have an isolated vertex? If we have, for example, another vertex here, v3, for example, if we have v3, then the degree of v3, what will be the degree of v3? Obviously we see how many edges are incident on v3. So there are no edges which are incident on v3, therefore the degree of v3 is 0. So if we have isolated vertices in any graph, then the degree of all those isolated vertices will be 0. Here we have a graph, as we have discussed in the previous example. Here, how to calculate degree of a vertex and how to calculate the degree of a graph, we have already discussed it. Here is another example. We have this a graph G, we say it a graph G. We have 3 vertices and 3 edges in this graph. So we shall calculate degree of all the vertices. Degree of v1 is 0, because as I have told you, v1 is isolated and isolated vertices have degree 0. So degree of v1 is 0, degree of v2 is 2, and degree of v3 is 4. Here is a loop, and loop is counted twice, so the total degree of G is degree of v1 plus degree of v2 plus degree of v3. So we have the degree of this graph is equal to 6. Now there is a theorem which is called handshake theorem. It says that if G is any graph, then the sum of the degrees of all the vertices of G equals twice the number of edges of G. Obviously, specifically, if the vertices of G are v1, v2, so on, vn, we have n vertices in a graph G where n is a non-negative integer, then total degree of G is degree of v1 plus degree of v2 plus so on plus degree of vn, and this could be 2 into the number of edges of G. You can see the proof of this theorem in the book of Discrete Mathematics by Susanna. This theorem is obvious, but you can see the proof of this theorem. So the total degree of G is basically 2 times the number of edges in G. For example, here in the previous example, how many edges we have in this graph? E1, E2 and E3. We have 3 edges, so the total degree of this graph will be 2 into number of edges is 3. So this is 6, so 6 is equal to 6. Why this is so? Because every edge is incident on 2 vertices. E1 is basically, if E1 is an edge, then obviously it will be incident on 2 vertices. For example, here E1 is incident on V2 and V3. So 1 degree, it will contribute 1 degree here in V2, and it will contribute 1 degree here in V3. So every edge contribute 2 degrees in the graph. So therefore we can write, and for a loop it is basically incident on V3 2 times, because the endpoints of this edge E3 is V3 and V3. It is incident on V3 here and here, so it contributes also 2 degrees in the graph. So we can write that the total degree of any graph G is basically 2 times the number of edges. We can draw another conclusion from this, that we have studied this in basic number theory, that if a number is a multiple of 2, it is an even number. So here the number of edges of G is basically an integer. It could be negative, it could be even, it could be odd, but it is multiple of 2. That is, we can write it as 2k, where k belongs to Z positive. So the graph, the degree of G can be written as 2k, where k belongs to Z plus. So we can draw a conclusion from here that the degree of any graph G is always even. That is, the total degree, you can say, degree of any graph G is always even. So this is another conclusion we can draw from this theorem. Now, what is a walk on a graph? This is not a usual walk which you do in parks and in your homes and in your offices, but it's a concept of a walk in graphs. That is, how we can travel from one vertex to some other vertex, or from one vertex to the same vertex in the graphs. Let G be a graph and let V and W be any two vertices in the graph G. A walk from V to W, that is, we have to go from vertex V to the vertex W, and V and W are any two vertices in that graph. A walk from V to W is a finite alternating sequence of adjacent vertices and edges of G. That is is a finite alternating. Is finite obviously because graphs are always we study in this course are finite graphs. That is, they have finite many vertices and finite many edges. So a walk from V to W is a finite alternating sequence of adjacent vertices and edges of G. What is alternating sequence? Alternating sequence means first we write vertex, then edge, then vertex, then edge, then vertex, then edge, and so on. This is why we write here alternating sequence. That is, one time we write edge, one time we write vertex. So this is an alternating sequence of vertices and edges, adjacent vertices and edges of G. Thus a walk has the form. Any walk, if we say that a graph G has n vertices, v1, v2, so on, vn, v0, v1, v2, so on, vn, and edges e1, e2, so on, en, then a walk can be written as this: v0 first vertex, we have to travel from v0 to vn. That is, we can say here that v0 is v and vn is w. So if we have to travel from v to w, then first we write v1, v, then edge which is adjacent to v, and then vertex which is adjacent to e1. You can say this. So a general walk has the form v0, e1, v1, e2, so on, vn minus 1, en, and vn, where the v's represent the vertices and e's represents the edges. Here we can say v0 is v and vn is w. And for all i2, i1, 2, and so on, n, vi minus 1 and vi are the endpoints of EI. Here basically if you write an edge here E1, then V0 and V1 must be the endpoints of E1. You cannot write here an edge E1 such that its endpoints are not V0 and V1. Similarly, if you write here E2, then its endpoints in the graph must be V1. Here you can write V2. So E2 has endpoints V1 and V2, and so on. En must have endpoints Vn minus 1 and Vn. So this is what you have to care about when you try to write a walk from one vertex to some other vertex. The trivial walk from V to V consists of a single vertex V. That is, if you have an isolated vertex in a graph or some other vertex which is not isolated, then if you this is a vertex V, then V to V, that is, we do not move here. A walk from V to V, that is standing still, is basically called a trivial walk from V to V, which consists of a single vertex. Now we discuss some of the definitions which are related to the walks. First definition is the definition of trial. A trial from V to W is a walk. Now these are particular types of walks in a graph, and a trial from V to W is a walk. Just remember it that all these definitions are basically, in general, they are walk, but here these are particular type of walks. A trial from V to W is a walk from V to W that doesn't contain a repeated edge. That is, if in a walk edges are not repeated, that is, every edge is used or written exactly once, then this trial walk will be called a trial from V to W. Here in this definition they do not specify about the vertices, so vertices may be repeated, may not be repeated. We don't see the vertices, but we have to see that any edge must not be repeated. So such type of walk is called a trial. The next is a path from V to W is a trial. A path, now we have a sub definition of trial which is called a path, and path from V to W is a trial. A trial is also a walk, so this is another particular walk also. A path from V to W is a trial that doesn't contain a repeated vertex. Now here they have restricted the vertices also, that vertices should not be repeated. Now here in a path we have both conditions. Edges must not also be repeated and vertices are also not repeated. That is, a path from V to W is a trial. That is, to investigate whether a given walk is a path or not, first we have to check whether it is a trial, that is, there must not be a repeated edge. Then we check there is not any repeated vertex, because this is a sub definition of trial. So first a walk should be a trial, and then we investigate whether it is a path or not. So next is a closed walk. What is closed walk? A closed walk is a walk that starts and ends at the same vertex. Now here it's basically a sub definition of a walk. It doesn't have to be a path or a trial, but in the second definition a path must be a trial first, and then we shall see whether it is a path or not. So a closed walk is a walk that starts and ends at the same vertex. Here a walk is an alternating sequence that starts and ends that may start and end at a different two different vertices, but a closed walk is a walk which starts and ends at the same vertex. The next definition is a circuit. What is a circuit? A circuit is a closed walk. Now, a circuit must be a closed walk, that a circuit should start and end at the same vertex. So it is a closed walk that contains at least one edge and doesn't contain a repeated edge. This is same condition as a trial, but here in a circuit the starting and ending point must be same, but in a trial the starting and ending point they may differ, they may be different. So a circuit is a closed walk that contains at least one edge. It should contain at least one edge. This is another condition, and circuit should not contain a repeated edge. So next definition is a simple circuit is a circuit that doesn't have any other repeated vertex except the first and last. Now, in the definition of circuit there is no condition on vertices, that is a vertices may be repeated, but the starting and ending point must be same, and other vertices may be repeated. But in a simple circuit it should be a circuit first, that is it must contain at least one edge and it doesn't contain any repeated edge. Next, a simple circuit does not have any other repeated vertex except the first and last. So this is basically a definition of a simple circuit. So let's see all these definitions, like in a table what are the conditions in a walk, trial, path, and what is the difference between all these conditions. So here in the form of a table we can understand better what is allowed in a walk, in a particular type of walk, and what is not allowed in that particular walk. So if you see walk, what is a walk? Walk, in a walk a repeated edge is allowed, a repeated vertex is allowed, starts and ends at same point is allowed, because they here in the definition of a walk they doesn't mention here that a walk from V to V, we cannot take the starting and ending point same, so we can take starting and ending point same. So must contain at least one edge. This condition is not necessary, it could contain only one vertex, which we call a trivial walk, as we have discussed in the definition of a walk. It's not necessary that a walk contains an edge. Now the next definition, trial, is basically in this trial repeated edge is not allowed, repeated vertex is allowed, starts and end points are same, it is also allowed in the definition of a trial. A walk from V to W that doesn't contain a repeated edge, so this is the only condition in the definition of trial. Next is the definition of path. In path, first of all, a path should be a trial, that is it should not contain any repeated edge, and further definition is it should not contain any repeated vertex. So here is also we have no. Starting and end points at starting and ending point may be same. Here starting and ending point must not be same. Is a trial doesn't contain a repeated vertex. Here if we take the starting and ending point same, then the one vertex will be repeated, so it violates the definition of path. So repeated vertices or starting and ending point is not allowed here also in a path. And must contain at least one edge. No, there is no condition here. What is a closed path? Repeated edge is allowed, repeated vertex is allowed, starting and ending point must be same, that's why it's called a closed walk, and must contain at least one edge, it's not necessary. Circuit, in a circuit repeated edge is not allowed, repeated vertex is allowed, starting and ending point must be same, and must contain at least one edge. Yes, there is a condition in a circuit that it must contain at least one edge. And the last definition, simple circuit, repeated edge is not allowed because it must be a circuit first, and then we shall see whether it is a simple circuit or not. A repeated vertex, only first and last is allowed, other verses must not be repeated. Starting and ending point must be same and must contain at least one edge, because it must be first a circuit and then we shall see whether it is a simple circuit or not. Now we see all these definitions with the help of examples. We are given a graph, this, the notation, some of the notations which we usually use in walks. In the graph below, the notation E1, E2, E3, E1, E2, E4, E3 refers unambiguously to the following walk. That is, this walk can be written as this. If we write a walk V1, E1, V2 here, we can write V1, E1 because endpoints of E1 are V1 and V2, so therefore we write here V1, E1, V2. Next, either we can write V2, E2, V3 or V2, E3, V3. So here he has written E2, V2, E2, V3, and then V3, E4, V3, V3, E4, V3, and then V3, E3, V2. So this is basically a walk, and this walk can be written as also E1, E2, E4, E3, because E1, E2, E4, E3. So instead of writing an alternating sequence of vertices and edges, we can write where there is no some confusion, we can write such walks by denoting only the edges, by writing only the edges. So here on the other hand, the notation E1 is ambiguous if used to refer to a walk. It could mean either, if we write only E1, then it could create confusion, that is this could be written as V1, E1, V2 or V2, E1, V1. So if there is no confusion in the walks, then we can write instead of writing alternating sequence of vertices and edges, we can write simply the edges also in the sequence. So this is another notation for the walks. In this graph, the part B of this example, the notation V2, V3 is ambiguous. In this graph, if we write instead of alternating sequence of vertices and edges, we write only the vertices V2, V3, then what does it mean? V2, V3, it could be V2, E2, V3, and it could be V2, E3, V3. So there is a confusion whether it's this walk or this walk. So on the other hand, in the graph below, the notation V1, V2, V2, V3, what does it mean? V1, V2 and V2, V2 means there must be a loop here. That's why we are writing this vertex 2 times, and then V3. There is no confusion in this notation, so we can write walks where there is no confusion by writing only the vertices like this, and where the loop can be written as we repeat this vertex 2 times to the walk, and this represent the same walk as we write this V1, E1, V2, E2, V2, E3, V3. So this refers the same walk as we write here. So where there is no confusion, there is no ambiguity, we can write a walk by writing only the edges or by writing only the vertices. So these are some other notations for writing walks So let's now investigate what with the help of examples, what are trials, paths, circuits, and closed simple circuits and closed walks. In the graph below this, determine which of the following walks are trials, paths, circuits, or simple circuits, or closed walks. Now first is basically here given V1 E1 here. Here we have V1 E1 here, V2 here, E3 here, this is the E3, V3 here, E4, this is E4, we again reach at E3, E5 and V4. So this is basically, first of all, this is a walk from V1 to V4. Now what is this walk, whether it is a trial, path, circuit, or simple circuit? So the first, in part A, the walk has a repeated vertex. Here we have repeated vertex. What is the repeated vertex? V3 is repeated here 2 times, that is, it comes 2 times but doesn't have any repeated edge. It doesn't have any repeated edge, so therefore it is a trial. Therefore it is a trial from V1 to V4, but it is not a path because it has one repeated vertex, one V3 vertex is repeated here, so it satisfies the conditions, the properties which are defined in the definition of trial. Therefore the first walk in the part A is basically a trial. It's not a path because there is a repeated vertex in this walk. Next, in B part, we have E1, E3, E5 and E. We reach here and we come back here, and then E6. Basically this is E1, this walk is this, E3, we go E5 here, and then we come back here, E5 again, and then E6. So here in this walk we have a repeated edge. In this we have a repeated edge, and there must also be repeated vertices. E3 will be repeated, yes, because V2 E3 V3 and V3 E5 V4, and then V4 E5 V3, and then V3 E6 V5. So in an explicit way we can write this as V1 E1 V2 E3 V3 and E5, and then V3, yes, then E5, no sorry, here V4 V3 E5 V4, and then E5 V3 and E6 V5. So explicitly this E1 E3 E5 E5 E6 can be written as. So now there is a repeated edge here, V3 V3, and there is a repeated vertex, and there is a repeated edge here. So this is just a walk from V1 to V5. It's not a trial because there is a repeated edge and there is also repeated vertices. So it's just a simple walk from V1 to V5 because vertices and edges may be repeated only in the walk, not in a trial, not in a path. In a trial, edges cannot be repeated. In a path, vertices cannot be repeated. Here both edges and vertices are repeating, therefore it's a simple walk from V1 to V5. And next, this in C part we have V2 V3. It starts from here, this walk starts from here, and we have this V2 V3 and then V4 and then V5 here and then V6 here, and then V2 here. So we start at V2 and we end at V2, and no edge and no vertex has been repeated here, so this must be a simple circuit. And there are some other possibilities here. In C part, this walk starts and ends at V2, contains at least one edge. We can see that in this part C, the starting point is V2, ending point is V2, and this will be, the starting point is here. From V2 we go to V3, from V3 to we go to V4, from V4 to we go to V5, and then from V5 to V3 here, and next we go to V6 and then V2. So here we have a repeated vertex, but no edge has been repeating here. So this could be a circuit because it contains at least one edge, the starting and ending point is same, and no edge is repeating, but versus V3 vertex is repeating here. So this is a walk first, and then it must be a circuit. So we can see here the solution. This walk starts and ends at V2, contains at least one edge, yes, and does it have a repeated edge? Yes, it doesn't have any repeated edge, so it is a circuit. Since the vertex V3 is repeating in the middle, it is not a simple circuit. So this equivalently, this can be written as V2, V3, V4, V5, V3, V6, V2. This can be written as V2, and we go to V3, and in the middle we write E3, V3, and then we go to V4, and from V3 to V4 we have E5, so we write here V5 and then V4, and then from V4 to V5 here we have E10 between V4 and V5, so we write here E10 and then V5, and from V5 we go to V3, and there is E6 from E5 to V3, so we write here E6 and then V3, and then from V3 to we go to V6, here we have E7, V6, and then from V6 we go to V2 again, and in this we have E8 and V2. So this notation can be written explicitly in the form of a alternating sequences or a sequence of the vertices and edges like this. So this is basically a circuit, because vertex V3 is repeating here but no edge is repeating here. So this is therefore it is a circuit. In the D part we have V2, V3. It starts again from V2, V3, it goes here, then to V4, then to V5, then to V6, then to V2 again. So this can be written as V2, E3, V3, E5, V4, E10, V5, E9, V6, E8, V2. So this is how we can write it explicitly, and we can see here that no edge is repeating here, no vertex is repeating here, starting and ending point is same, it contains at least one edge, so it's a walk and it's a simple circuit because it satisfies all the properties of simple circuit. In this part, this is walk. This walk starts from V2 and ends at V2. Starting and ending point is same. Contains at least one edge. Doesn't have any repeated edge. Doesn't have any repeated vertex. So this is a simple circuit. So next is what? E part. V1, E1, V2, E1, V1. So What is this? It starts and ends at v1. It has one edge. Edges e1 is repeating, and v1 in first and last point is same. We have v2, so it could be a closed walk because starting and ending point is same, and edges are repeating, so this is only allowed in a closed walk. So in this is just a closed walk, starting and ending at v1. It is not a circuit because edge e1 is repeating, because in a circuit there is a condition that it must contain at least one edge, and edges must not be repeated, so it is not a circuit, it is a simple closed walk. In the last part we have v1. v1 is a trivial walk, as we have discussed in the definition of walk, that a walk from a vertex to itself is a trivial walk. So v1, the last part, is basically the first vertex of this walk is the same as its last vertex, but it doesn't contain an edge, and so it is not a circuit. It is a closed walk from v1 to v1, so it is also a trial from v to v1. It is you can say it's a closed walk, or you can say it is a trivial walk. You can say it here, a trivial walk also. Trivial walk. So next is, so I hope you have understood what is walk, what is the other definition: trial, path, simple circuit, closed walk. Now what is the connectedness? If we have graphs, so we must discuss what is the connectedness and disconnectedness. You can see that a graph, if you want to investigate whether a graph is connected or not, that is, all the vertices of the graph are connected by some edges, then how we can investigate this, whether the given particular graph is connected or not. So here is a definition which tells us whether a graph is connected or not. Let G be a graph. Two vertices v and w of G are connected. Any two vertices, you can take any two vertices in the graph. For example, we say them v and w are any two vertices of the graph G, and v and w of G are connected if and only if there is a walk from v to w. If and only if there is a walk from v to w. The graph G is connected if and only if, given any two vertices v and w in G, there is a walk from v to w. Symbolically, we can say that G is connected if and only if for all vertices v and w. That is, if we choose any two vertices in the set of from the set of vertices of that graph, vw belongs to v of G, there is a walk from v to w. If there is not a walk, then we cannot say that these graphs are connected. So there must not be a trivial walk. You can add this here, that there must not be a trivial walk, because trivial walks are could be the walks of isolated vertices also. If there is an isolated vertex, for example in this graph we have v4, you can write a trivial walk from v4. You can write this because it's a trivial walk, but this graph is not connected, because we'll discuss it later. For example, here we investigate the following graphs are connected or not. In the first graph, if we choose any two vertices in this graph, there is a walk from first vertex to the second vertex. For example, here you choose v2 and v6, so there is a walk from v2, v3, v4, v5, v6. There is a walk. Now here in this graph, if we choose v1 and v4, then there is no walk from V1 to V4. So this graph second is not connected, but the first graph is connected, because if we choose any two vertices in this graph, there exists some walk from the first to second vertex. But in this graph we cannot say that for all vertices V and W there is a walk from V to W, because if we choose V2 V4, V5 V2 V4 sorry, or V5 V2, if we choose V5 and V2, there is no walk from V2 to V5. But if we choose V5 and V7, then there is a walk from V5 to V7. But only these four vertices satisfy the condition of walks. But if we choose V3 V6, V3 V4, V2 V4, there is no walk between these two vertices, so this graph is not connected. If we see this graph here, there is no walk between V1 and V2, V1 and V3, V1 and V6, or V4 and V2, V4 and V5, because this graph can be redrawn as this. Here the previous graph was like this. Here we have vertex, here we have vertex, here we have vertex, here we have vertex, here also, here also. Here we have V1, V4, here we have V2, V3, V6, V5. So here we don't have any vertex. We don't have any vertex. So this vertex and this vertex are not connected here by using any edge. So this graph can be redrawn like this. Now you can see that these components basically are not connected. Here there is no walk from V1 to V6, from V1 to V3, from V1 to V5. So this how we can say that this graph is not connected? If there exist at least 2 points, अगर कम से कम 2 पॉइंट्स हम किसी भी ग्राफ में अगर फाइंड कर सकें, कोई से 2 पॉइंट्स, अगर एक केस भी ऐसा हो, मींस V1 और V5 के दरमियान कोई वॉक नहीं है, so it's enough that this graph is not connected. We don't need to check other points, other vertices. If you can find two vertices and there is no walk between these two vertices, then you just simply say that this graph is not connected. So this is how we can check the connectedness of the graphs. Now there is a result relating to the connectedness, which is a theorem. Let G be a graph, and the first part, this I don't include here the proof of this theorem. You can see the theorem, the proof of the theorem in the book of Discrete Mathematics by Susanna. If G is connected, then any two distinct vertices of G can be connected by a path. So it's obvious. If G is a connected graph, then if we take any two vertices, then we can construct a walk from first to then any two distinct vertices of G can be connected by a path. That is, we can create a path from first vertex to second vertex. What is a path? Path is a trial which doesn't have any repeated vertices. Edges are also not repeated because it must be a trial also. So the second, in the B part, if vertices V and W are part of a circuit in G. If V and W are part of a circuit in G. Now remind the definition of a circuit, that is starting and ending point must be same, at least one, it contains at least one edge, and it must not contain a repeated edge. So if you have two vertices V and W, this is part of a circuit in G, and one edge is removed from the circuit, then there still exists a trial from V to W in G. So what is trial? Trial is basically a walk in which edge is not repeated. So in a circuit is basically a closed walk. If you remove one edge, then still there is a trial from V to W. So this is obviously, if you just imagine a little here, for example, here we have a circuit whose starting and ending point is same, then edge from here V1, V2, V3 and V1. If this is a circuit here, for example, starting and ending point same, it contains at least one edge, this one and this one, and if we remove this edge, for example this edge, and V2 and V3 is a part of this circuit, then still we can remove this edge also, then still there is we can write a trial which is V2 E, for example this is E2, then V2, E2 and V3. This could be a trial from V2 to V3. So we can define a trial if V and W are part of a circuit in G and one edge is removed from that circuit because it's a closed walk, then there still exists a trial from V to W in that graph G. It's also obvious, but you can see the proof of this theorem in the book. The C part is if G is connected and G contains a circuit, then an edge of a circuit can be removed without disconnecting G. It's also obvious. For example, here this is a graph, it contains a circuit as we have written this. If we remove one edge, this one, either we remove this, either we remove this, either we remove this, this graph still will be connected graph because it contains a closed walk. If we remove one edge, it will be still connected graph. It's also obvious, but you see the proof of this theorem to confirm this claim. Next is what is a connected component of a graph. A graph H is a connected component of a graph G if and only if connected component H is a subgraph of G, H is connected, and no connected subgraph of G has H as a subgraph and contain vertices or edges that are not in H. You can see that largest subgraph of G which is connected is basically the connected component of that graph G. For example, this you may confuse this third step. A connected component of a graph is basically it should be subgraph of G, it should be connected, and no connected subgraph of G has H as a subgraph. Means there is no larger subgraph of G which contains H. That is, you can say H should be largest subgraph of G which is connected. For example, here in this previous case here, this is a connected component of this whole graph because it is connected, it is subgraph of this, it is connected, and no other connected subgraph of G contains this graph, and you can say this no connected subgraph of G has H as a subgraph. So if you say that this graph contains this H, now this is basically this graph K, for example, this is also a subgraph of G, but it contains H, but it is not connected. So H is the largest subgraph which is connected and subgraph of G, and no other connected subgraph of G which contains H. So therefore H is a connected component of this graph. Similarly, this is also a connected component of this whole graph G, and this is also a connected component of whole graph G. So there are 3 connected component of this whole graph G. Similarly, this also, you have one this connected component, one this connected component, and one this connected component of this whole graph G. So it has 3 connected component. For example, this is H1, this is H2, this is H3. So what is connected component of a graph? Basically a subgraph. It is a subgraph of G. It should be connected, and no other connected subgraph of G has H as a subgraph, and it contains vertices or edges that are not in H. For example, here the same example we have discussed in here. This is approximately the same. If we take this as H, and this whole graph is the graph G. Now G has 3 connected components. For example, one is this, second is this, and third is this. If we say this H1, this is H2, and this is H3. All these subgraphs are connected. They are subgraphs of G, and no other connected subgraph of G which contains H and contains more vertices and edges which are not in H1, either H2 or H3. With H1, H2 and H3 with vertices set V1, V2 and V3. So H1, the vertices in H1 are this V1, V2, V3. Vertices in H2 is only the vertex V4. Vertices in H3 is V5, V6, V7, V8. And the edges set in H1 is this. Edges set in H2 is basically there is no edge in H2. So this is 5, this is empty set, and edges set in H3 is this E3, E4 and E5. So these are all the connected components of the graph G. So for today it's I think enough. So we summarize what we have studied today. Today we have discussed subgraphs and what is degree, how we calculate the total degree of a graph. We have discussed walks, trials, paths and circuits. And we have discussed also the connectedness of a graph and what are the connected components of a graph. Today we are unable to discuss Euler circuits and how to construct an Euler circuit. In the next lecture we shall continue this, and first we shall discuss Euler circuits. First we shall discuss Euler circuits and then how to construct a Euler circuit. And then we shall discuss some other topics also of the graph theory in the next lecture. So until the next lecture, Allah Hafiz.